It is Saturday afternoon here on the East Coast, which is absolutely the perfect time to talk about the extremal of the Alexandrov-Fenchel inequality for convex polytope, and this is a joint work with Ramon van Hendel. And before I begin, let me thank the organizer for inviting me to give this talk and also for a very nice trimester program. It has been wonderful. Uh, let's start by stating the Alexandrov-Fenchel inequality, which is a statement for mixed volumes, which I will remind you what they are shortly, but for those of you who already know what they are, here's a statement. So we have n convex bodies in our n, KL to C1 Cn minus 2, and the inequality is telling us that the mixed volume of VKL C1 to Cn minus 2 squared is greater than VKK C1 to Cn minus 2, so these bodies are always remain fixed, times VLL C1 to Cn minus 2. And the basic question that we're interested in is the equality cases of this inequality. By that I mean, for which bodies KL C1 to Cn minus 2 do we have equality in the Alexandrov-Fenchel inequality? So before we discuss this problem, let's remind ourselves what are mixed volumes. So if we have m bodies in our n, and we have some non-negative numbers T1 to Tm, then if I look at the volume of the Minkowski sum, the function of these Ti, then that's a polynomial. And the coefficient of these polynomials are mixed volumes. So what is a Minkowski sum? If you have two bodies, K and L, and two non-negative numbers, A and B, the definition is just that it's a set of all points ax plus by, where x is in K and y is in L. And here's a quick picture. We take here K to be this cube, and A, let's say 1, and L is the unit ball, and B is epsilon, which we think about as being very small. So when we add the two together, we just place this little ball inside the cube and on the boundary of the cube. So when we place it inside the cube, nothing really changes, but when we place it on the boundary, that smooths out the body. So here's a resulting body, and you can see the edge colored in yellow is mapped to this rounded edge, and similarly here for this vertex, which is mapped to this rounded vertex, if you will. This is the Minkowski sum. So it's a basic result in convex geometry that if you look at the volume of the Minkowski sum, the function of the Ti, that's a homogeneous polynomial of degree n. And because we are in dimension n, so this is the sum over all n indices, which take place from 1 to m, because we have m bodies. And this is, we have here a multiple of Ti1 to Tin, so this is of degree n. And the mixed volume, that's the coefficient which depends on the bodies Ki1 to Kin. And some basic properties of mixed volumes are they're always non-negative, they're symmetric, which you can see just from looking at the definition because the left-hand side is symmetric. If you plug in the same body in these n slots that the mixed volume take, then you just get the volume of the body. And if you plug them all to be the same, except one of them, which we take to be the unit ball, which I denote by B, you get something which is proportional to the surface area of K. So the reason why we care about the equality cases of Alexandrov-Fenchel inequality, because these are extremal structured. So let me start with an example, the isoperimetric inequality in R3, which is a consequence actually of the Alexandrov-Fenchel inequality. So the inequality is telling us that the surface area of K is lower bounded by the volume of K, some power, and the volume of B to some power. And we know that equality holds if and only if K is equal to B, the unit ball, up to dilation and translation. So in words, what this means is that among all bodies that have a fixed volume, the ball is the one which minimizes surface area. And you can see that just because if you fix the volume here on the right-hand side, and you look at all bodies which have this volume K, and you asking which one will have the smallest surface area of all the bodies with this fixed volume, then obviously it would be the one which will attain equality in this inequality. So the fact that equality holds in the isoperimetric inequality, if and only if K is a unit ball, means, again, up to dilation and translation, mean that among all bodies of fixed volume, the ball minimizes surface area, which is a very fundamental result in geometry and also has, of course, implications to physics, etc. But the equality cases of Alexandrov-Fenchel inequality can be quite strange, unlike the one for the isoperimetric inequality. So here's a very basic one, which is perhaps a bit more complicated. Maybe you can think of it as the next one after the isoperimetric inequality. So my reference body here is C, any convex body, and here I have B and C. So I have VB. I have the mixed volume of B, C, C, and here BBC and CCC, which is exactly the form of the Alexandrov-Fenchel inequality. And I remind you that this term is nothing but the volume of C, and the term here on the left is proportional to the surface area of C. And this middle term is proportional to the mean width of C, which we don't have to define what it means. It just, the intuition is just how wide is the body on average. But at any rate, this is a basic geometric quantity associated to the body C. And characterizing the equality cases answers the questions among all bodies that have a fixed product of volume and mean width, which one will minimize surface area? And you can see that unlike, so of course you can take the ball here, that would be one example, or any dilation and translation of the ball. But the point is that there are in fact infinitely many solutions, unlike in the case of the isoperimetric inequality where you have only one solution. Here you have infinitely many. Not only do you have infinitely many, but they can be quite strange. This is an example of one of them. These are called cap bodies, which you form by taking a ball and putting all these cones on top of it so that they don't intersect. And there are many of them, infinitely many in fact. And all of them will have a small surface area for a given product of volume and mean width. Here is yet another example of a strange equality case of the Alexandrov-Fenchel. If you take K, L, and C to be these bodies, you will get equality. And here's another one. They don't have to necessarily be these ball-like shapes. You can also take polytopes. And here you take C to be a cube, and K and L to be the cube where you chop off some of the vertices and you put a facet there. So the general question that we're interested in is, when do we have equality case in complete generality? So this is a problem which goes back quite a long time ago. It goes back to the work of Minkowski in 1903. He was the one who developed the theory of convex bodies. And in fact, he also discussed this particular equality case. He states that these are the only equality cases of this inequality. He didn't prove it. The proof really came only in 43 by Bullock, who actually proved more than that. And he characterized the equality cases when the bodies L and C1, 2Cn minus 2 are all the same. And for a long time, it wasn't even clear whether one can come up with any natural characterization or sensible characterization of the equality cases, exactly because, as we saw, they can be quite complicated. But Schneider in 85 formulated conjectures in complete generality, at least when the bodies are full dimensional. When the bodies are not full dimensional, then it was known that there are more equality cases. There wasn't even a conjecture what they should be. And he also settled some special cases. And after that, not much has been done until in 2019, together with Ramon, we characterized the equality cases in the case where the bodies you want to see n minus 2 are all the same, but it can be an arbitrary convex body. And that requires some analytic theory because the body can be arbitrary, but we did not handle the case where the bodies are different, which is part of where the complexity is coming out of. So today I want to talk to you exactly about that. So this is a recent paper that I have together with Ramon, and here's the name of it and the link in the archive. And I just want to summarize very briefly what we did there. I won't have time to actually discuss the result, but let me just say a few words about it. So we characterize equality cases where the bodies C1 to Cn minus 2 are any arbitrary full dimensional polytope. And we also did when the arbitrary low dimensional polytope. So really the result is that we characterize the equality cases of Alexandrov-Fenchel whenever C1 to Cn minus 2 are any arbitrary polytopes. But I distinguish between the two because you get new equality cases in the case where the polytopes are low dimension. We did, in fact, a bit more. You can have all kind of mixed cases. For example, you can take the M of the bodies to be the same and be any arbitrary convex body. It doesn't have to be a polytope, and the rest of them to be smooth. And a special important case is the case of square mass integrals. So we also settled the equality cases for square mass integrals, which are almost characterized, but not quite. And you can also take them to be combinations of full dimensional smooth bodies, zonoids, and polytope, and all kind of things. And I'm not going to get into it. You can find it all in the paper. And maybe something which is a bit interesting is to mention some applications and going beyond convex bodies. So our work allowed us to characterize the equality cases of low concave sequences in combinatorics. This is in the theory of partially ordered sets. And then we also tried to have some broader connections, which are more speculative, to Hodge-Riemann relations. So let me just say maybe a few words about the low concave sequences, because I don't have the time to actually explain to you what are the equality cases of the Alexandrov-Fenchel. This requires some work. But there's kind of a general phenomena about low concave sequences. So before I tell you the phenomena, what is a low concave sequence? So we have non-negative numbers, a0 to an, and they're low concave if we have this relation, which of course looks like the Alexandrov-Fenchel inequality. And it's a ubiquitous phenomena. People have realized that they show up all over the place, meaning a lot of polynomials have coefficients which are low concave, and linear extension of posets are low concave. And here I put check marks near cases where we know that they're low concave, but there are other cases, this example, where it's only conjectured that the coefficient of this polynomial are low concave. And the question, why is that? Why do we have so many of them? And there's a recent emerging answer, which a number of people have worked on, which has to do with some underlying algebraic structure that satisfy the Hodge-Riemann relations. We don't have the time to get into it, but here's a reference for it. And they show up in many places. Of course, the polytope algebra, this is kind of the Alexandrov-Fenchel inequality. So maybe kind of a vague question to leave, to finish with is, what we did, we were able to use the fact that we characterize the equality cases of the Alexandrov-Fenchel inequality and then use some correspondence due to Stanley between convex but mixed volumes and combinatorial sequences to also characterize the equality cases of low concave sequences, meaning suppose I know that for some I have equality here. What does that tell me about the sequence? So we did such a case for the setting of posets. And one could try and dream whether there is a general theory which tells us something about extremal low concave sequences, meaning if you have a low concave sequence, if you know that you have equality somewhere in the sequence, what does that tell you about the sequence itself? So maybe in such a complete generality, this question is a bit hopeless, but in the paper, we kind of made a first step towards it. Anyone who's interested can look there, and also please feel free to reach out if you have any questions. So this is the end, and let me stop here with this nice picture of a cat body. Thank you.